Welcome to This Explainer. Today, we're decoding a massive breakthrough coming out of MIT and ETH Zurich. And honestly, this one finally fixes what might just be artificial intelligence's biggest, most frustrating flaw, its memory. We are talking about a fundamental shift here, moving from training these static, frozen brains into systems that can actually accumulate knowledge over time, just like we do. So let's dive right into this.
Imagine, just for a second, if learning how to ride a bike completely erased your memory of how to drive a car. You sit down in the driver's seat, and your brain simply has no idea what a steering wheel even does anymore. No way, right? It sounds totally absurd for a human. But sadly, this is the exact literal reality for today's foundation models. Every single time we try to teach them something new after their initial training, we risk totally wiping out their existing capabilities.
In the AI field, we call this catastrophic forgetting. It's exactly what it sounds like. A model acquires a new skill, but its pre-existing capabilities just rapidly degrade. Poof, gone. And the crucial thing to understand here is that this fundamentally happens because of how we currently teach AI new tricks. We primarily use a method called supervised fine-tuning, or SFT. Now, SFT has been the industry standard for taking a smart base model and adapting it to a specific task. But, well, it has a massive architectural blind spot. To understand why this happens, we have to look at how these models actually learn. You see, SFT is what we call an off-policy trap. This basically means the AI is just blindly memorizing expert demonstrations. Think of it like an actor reading a really rigid script. It doesn't actually learn how to solve a problem. It just learns how to mimic a specific answer. So the moment it faces a real-world scenario that deviates even slightly from that script, it drastically drifts and completely fails. But researchers have proposed a genius solution: self-distillation fine-tuning, or SDFT. SDFT is on policy. This means the model learns by generating its own successes and its own mistakes. It actively reasons through the problem, rather than just copying a cheat sheet. This illustrates the difference perfectly. See that plunge downward with standard SFT? It gains accuracy on a new task, sure, but it completely erases its prior knowledge to get there. It's a huge trade-off. Now, look at the SDFT performance. It pushes straight to the right. It gains the exact same or even better accuracy on the new task while keeping its prior performance completely stable. Literally zero catastrophic forgetting. Now, exactly how SDFT pulls off this magic is super fascinating. It solves this AI amnesia by turning the model into both the student and the teacher at the exact same time. Instead of relying on an external, rigid dataset to force updates, SDFT leverages the foundation model's own incredible in-context learning capabilities. It essentially builds a powerful internal monologue, allowing the model to generate its own robust training signals. Let's break down this process, because it is wonderfully elegant. For every single query we want to train the model on, the system creates two versions of itself. First, a teacher. This teacher is conditioned on the prompt and the expert demonstration, so it sees the perfect answer and completely understands the intent. Second, a student version, which only sees the raw prompt. The training process then forces the student to minimize the divergence between its own natural token distribution and the teacher's distribution. In plain English, the student learns the precise reasoning path of the teacher, distilling that customized logic right into its own weights. By using itself as the teacher, the model completely avoids the massive behavioral drift that actually causes catastrophic forgetting in the first place. We measure this drift in something called NATS, which basically calculates the divergence from the base model's original brain. Standard SFT causes a massive deviation of 1.26 NATS. It essentially rewires the model's brain so much that it forgets its past. But this self-teaching SFT loop, it keeps the logic incredibly close to the original base model, deviating by only 0.68 NATS. It learns the new skill while keeping its core identity entirely intact.
So, you might be wondering, how does this work when we want to inject brand new, factual knowledge that the model has literally never seen before? Well, the researchers tested this by injecting a corpus of Wikipedia articles about natural disasters that occurred in 2025. This is data completely outside the model's pre-training. When they conditioned the internal teacher on both the text of the article and the correct answer, the model's strict accuracy absolutely skyrocketed. It jumped from a baseline of 37% all the way to 89% strict accuracy. Incredible!
But here's where it gets genuinely astonishing. I mean, it's one thing to answer a direct question about an injected fact, right? It's another thing entirely to actually integrate that fact into your worldview. To test this, researchers asked out-of-distribution questions. They wanted to see if the AI could use the new knowledge to answer indirect questions. Standard SFT really struggled, hitting 80%,
which basically means it was mostly just memorizing specific answers. But SDFT, it hit a near-perfect 98%. It didn't just memorize, it actually absorbed and understood the new reality. Okay, let's see how this builds into the ultimate test of an AI's memory, sequential training. This is basically the holy grail of continual learning. Can we teach a model a highly specific skill, like tool use, and then immediately teach it undergraduate-level science reasoning, and then immediately follow that up with complex medical reasoning, one right after the other? Well, here is the SFT baseline for that sequential test, and honestly, it is a total disaster. The model learns tool use beautifully at first, but the exact moment researchers start training the model on the second subject, science, that tool use knowledge violently crashes back down to zero. Then it learns science, but as soon as medical training starts, science crashes. It's just this endless, frustrating, oscillating cycle of learning and immediately forgetting.
Now watch what happens with our breakthrough SDFT. The difference is staggering. As training progresses from tool use to science to medical, performance stays beautifully stable and consistently high. There's no crash, there's no off-policy memory wipe. This absolutely proves that the model is genuinely accumulating distinct, highly complex skills over a long horizon without regressing. It's actually building a true repertoire of abilities. We can see this success reflected across all three complex domains simultaneously through Pareto efficiency. Now, that's just a fancy way of measuring the optimal trade-off between retaining old knowledge and gaining new knowledge. Across science, tool use, and medical tasks, SDFT consistently dominates the top right corner here. It completely avoids the steep downward penalty that constantly plagues standard supervised training methods.
And, there's a really vital scaling law at play here, too. Because SFT relies fundamentally on the model's own in-context reasoning to act as the teacher, the quality of the training depends heavily on how smart the model is to begin with. When researchers scaled this test up from a 3 billion parameter model to 7 billion, and finally up to 14 billion parameters, something striking happened. The bigger the model gets, the wider its performance advantage over SFT actually becomes. Basically, the smarter the base model, the better it is at teaching itself.
As an incredible bonus to all of this self-teaching mechanism solves a massive headache for AI developers, training reasoning models when you don't actually have the reasoning steps written out. Usually, if you train a reasoning model on a dataset that only contains short final answers, the model's reasoning abilities just collapse. It gets lazy and learns to just blurt out short answers. But when researchers applied SDFT using only final medical answers, the model used its internal teacher to reconstruct the missing logic. Medical reasoning accuracy didn't just survive, it boosted from 31% up to a massive 43.7%.
What we are looking at here with SDFT is an active shift in the fundamental nature of artificial intelligence. We are moving away from AI as a static, frozen snapshot of data scraped from the internet and moving toward AI as a dynamic, lifelong learner that can accumulate skills sequentially, just like we do. So the question I want to leave you with today is this. As these models learn to never forget, continually stacking complex skills one on top of the other without any degradation, what limits truly remain on their evolution? Thank you so much for joining me for this explainer, and keep questioning what's possible.